morning. In this lecture, I'll solve some problem relating to Pelton wheel. The statement of the problem number 1 is a generator is to be driven by a small Pelton wheel with a head of 91.5 meter at inlet to the nozzle and the discharge of 0.04 meter cube per second. The wheel rotates at 720 RPM and the velocity coefficient of the nozzle is 0.98. If the efficiency of the wheel based on the energy available at the entry to the nozzle is 80% and the ratio of the bucket speed to the jet speed is 0.46, determine the speed of the wheel to jet diameter ratio, and the dimensionless power specific speed of the wheel. So now I'll solve the problem in the next slides. I'll solve the problem now. The quantities that are given: head H as 91.5 meter, flow rate Q 0.04 meter cube per second, rotational speed of the bucket or the wheel is 720 RPM, coefficient of velocity for the nozzle CV 0.98, overall efficiency eta 0 is 80%, bucket speed U divided by absolute velocity from the nozzle C1 is given as 0.46. We need to calculate U, bucket speed, wheel diameter to jet diameter d by small d, and specific speed ns. So these are the quantity we need to calculate from the given data. Now I'll solve. The eta 0 overall efficiency can be stated as power developed divided by power available So thus I can write power developed as P, power available, I can write mass flow rate into G into H. That can be written as density into Q is the volume flow rate, G into H. H is the available head. So thus I can say P is equal to eta 0 rho Q G into H. Eta 0 is given as 0.8. Rho I can write rho of order 10 to the power Q. Volume flow rate is given as 0.04. G can be taken as 9.81 and head available is 91.5. So if you do the calculation, you will get power as, please check the calculations, 28.72 kilowatt. So I have calculated power as 28.72 kilowatt. That's power developed. Now CV is given as, coefficient of velocity is given as 0.98. So I can write coefficient of velocity is C1, absolute velocity from the nozzle, divided by root over twice G into H. H is the available head. So from here, I can calculate C1. C1 is nothing but CV into root over twice G into H. We know all the values. CV is given as 0.98 into root over 2 into 9.81. H is given as 91.5. If you do the calculation, you will get C1 as 41.52 meter per second. Hence now U is equal to 0.46 into C1, because ratio of bucket velocity by absolute velocity of the jet is given as 0.46. So I can calculate U. Since C1 I have just calculated, put the value of C1 here. So U I have calculated, it is 19.1 meter per second. Now, again, I can write U is equal to omega, that is rotational speed of the disk, into D by 2. From here I can evaluate quill diameter D as twice U divided by omega, that is twice U divided by 2 pi n by 60. U I have evaluated as 19.1, so this should be 2i into 19.1 into 60 divided by twice pi. RPM is 720. Put all the value here. If you calculate, you will get D is equal to 0.507 meter. Just I have evaluated D as 0.507 meter. Now let's go to the jet area. A can be projected as Q flow rate by C1. A can be considered as flow area at the exit of the nozzle. Now I know the value of Q, 0.04. C1 is 41.52. If you evaluate this, you will get 0.963 into 10 to the power minus 3 meter cube. Just jet diameter can be given as D is equal to 4A by pi to the power half. So that is equal to root over 4. Area I have evaluated 0.963 into 10 to the power minus 3 divided by pi. If you do this calculation, you will get 0.035 meter. As I have evaluated the diameter, jet diameter. As diameter ratio can be projected as which is the wheel diameter, capital D divided by jet diameter is equal to capital D is 0.507 divided by 0.035. If you do the calculation, you will get 14.5. Thus, I have got the answer, first answer, which is diameter ratio, wheel diameter divided by jet diameter as 14.5. The next one is to evaluate dimensionless power specific speed. The dimensionless power specific speed can be expressed as Ns is equal to omega. Omega is the wheel rotational speed in radian per second into power by rho to the power half divided by GH to the power 5 by 4. Let me put all the expression. Omega is equal to 2 pi n divided by 60. That is 2 pi n is 720 divided by 60. This will be omega. Power I have evaluated as 28.72 into 10 to the 4 3 divided by rho is 10 to the 4 3 into half to the power half whole divided by G should be 9.81, head 91.5 to the power 5 by 4. Thus, put the value of omega here. Omega is coming as can be written as 2 pi n divided by 60. Then power divided by density to the power half, whole divided by, this is G, H to the power 5 by 4. If you do all the calculation, you will get the value of Ns as 0.082. It will be in radian. Thus, I have got the specific speed of the Pelton wheel as 0.082. Hence, I have evaluated all the answers that were asked. I'll solve the second problem now. The statement of the problem is the buckets of a Pelton wheel deflect the jet through an angle of 170 degrees, while the relative velocity of water is reduced by 12% due to the bucket friction. Calculate the theoretical efficiency from the velocity triangle for a bucket stroke jet speed ratio of 0.47. Under a gross head of 600 meters, the wheel develops 1250 kilowatt power when the loss of head due to pipe friction between the reservoir to the nozzle is 48 meters. The bucket circle diameter of the wheel is 900 mm and there are two jets. The nozzle velocity coefficient is 0.98. Find the speed of rotation of the wheel and the diameter of the nozzle if the actual wheel efficiency is 0.9 times of the theoretical wheel efficiency. The important points here that jet is deflected by an angle of 170 degree and the frictional coefficient for the bucket is 0.88. So you need to calculate theoretical wheel efficiency for a bucket to jet speed ratio of 0.47. Furthermore, the gross head is given at 600 meter. The losses in the pipeline is 48 meter and the power developed is 1250 kilowatt. Furthermore, coefficient of velocity is 0.98. We'll have to calculate the speed of rotation of the wheel, the diameter of the nozzle, and furthermore it's giving that the actual wheel efficiency is 0.9 times of theoretical wheel efficiency. Let me solve the problem. I'll draw first the schematic of the bucket and the nozzle. So this is the bucket having a speed U. This is the nozzle that creates a jet with a velocity C1. Now with this understanding, if I draw the velocity triangle for the bucket, what will be the inlet velocity diagram? U is the bucket speed plus W. W is the relative velocity at inlet, and U plus W1 would be equal to C1. So this is the C1. Hence I can write at the inlet C1 is U, that is bucket speed, plus W1 is the relative velocity of the flow with which it is entering to the bucket, right? So W1 is the relative velocity that is entering to the bucket, and W2 will be the exit relative velocity. So now if I draw the exit velocity triangle, this will be U, this is W2, and this would be C2. Now W will be deflected by an angle of theta. Theta is equal to 170 degree. So this is beta 2. Beta 2 will be 10 degree. Let me also assess what are the quantities that have been given. As I have already told, theta is given as 170 degree. So I can say beta 2 is 180 minus 170, that is 10 degree. W2 would be equal to K into W1. K is the friction coefficient for the bucket. It is given as 0.88 into W1. Furthermore, U by C1 is stated as 0.47. Gross head AG stated as 600 meter. Am I right? Head loss HF is 48 meter. Power produced P is 1250 kilowatt. Now we need to calculate efficiency of fuel, rotational speed, and diameter of the jet, right? Furthermore, this is CV is also given. CV as given as 0.98. So these are the quantity which are given. Hence, eta W, that is efficiency of the wheel, can be stated as power developed divided by energy available. I can write also specific power output. So this, if I put in terms of specific power output, so I'll get small omega or small w means specific power output divided by half C1 squared, that is kinetic energy of the jet. This is the expression for eta W, or I can say, if we say W, work output, divided by, I can say also, half m dot into C1 square. M dot is the mass flow rate through the bucket. Please note that I'm considering the one bucket, okay, and I'm considering a single jet, okay. In this problem, there are two jets, okay. So finally, if I calculate mass flow rate considering the total power, that is 1250. Please remember, this has come from two nozzles. Thus, now gross head is given as 600 meter. Losses in the pipeline also has been stated. So I can write now head available HE is equal to HG, that is gross head, minus head loss in the pipeline, HF. So therefore I can write 600 minus 48. If you calculate, it would be 552 meter. So I have evaluated which is the effective head available. Now I can define CV, that is coefficient of velocity, as C1 by root over twice G into HE. Thus from here I can write C1 is equal to CV into root over twice G into HE. I know the value of HE. I know the value of CV. So CV has been given as 0.98 root over 2 into 9.81 into HE is 552 meter. If you evaluate this, C1 I have got as 102 meter per second. Thus, what I have done here, I have drawn the velocity triangle or the velocity diagram, both at inlet and exit. I have defined eta W, and then I have evaluated available head HE from the available head, and CV I have calculated C1. Now let me proceed. So small w, that is power output, is equal to capital W by m dot is equal to, from the velocity triangle you can appreciate this will be u into c theta 1 minus c theta 2. Now look, c theta 1 is equal to u plus w1. C theta 2 from the velocity triangle would be equal to w2 cos theta 2 minus u, and as per the sign convention, c theta 2 would be negative because c theta 2 acts in the opposite direction of u, considering the velocity triangle. Thus I can write it would be equal to u minus w2 into cos beta 2. Now w2 can be written as k into w1, so u minus K into W1 into cos beta 2. So this is the expression for C3 theta 2. Put the value of C theta 1 here and right, and C theta 2 from here. So after putting the value of C theta 1 and C theta 2 in this expression, I get small w is equal to 1 plus K cos beta 2. I have taken W1 as common into U. Now again W1 can be written as, from this expression, W1 can be written as W1 can be written as C theta 1 minus U, and C theta 1 is equal to C1. So therefore this should be 1 plus K cos beta 2. This should be equal to C1 minus U into U, because C theta 1 is equal to C1. Now I know the value of K, I know the value of beta 2. I have estimated C1 and U, and thus I have estimated U rather. I am estimated also I know the value of C1. Just let me put the whole value here. So this is 1 plus K would be 0.88 cos of 10 degree. Let me put it in terms of C1. C1 U is 0.47 of C1, and again 0.47 C1, right up. So if you do this, it would be 0.465 into C1 squared. Please check the calculation. Now the theoretical eta W would be equal to small w divided by half C1 squared. So it can be 0.465 divided by 0.5. So if I do the calculation, I have got 0.93. Therefore, I got another answer, eta W theoretical, th suffix th means theoretical, is 0.93. This is another answer. Let me proceed further. Actual eta W would be now would be equal to 0.9 into theoretical eta W. That's theoretical eta W is 0.93 that I have calculated a minute before. It will be equal to 0.837. Therefore, the actual wheel efficiency I have evaluated as 0.387. Now, bucket speed, capital U, is 0.47 into C1. C1 I have evaluated, that is 0.47 into 102. I got U as 47.94 meter per second. So I got the values of U. Now this can be written as U is nothing but twice pi r in divided by 60. R is the radius of the wheel. So from here I can evaluate N. N is equal to 60 U divided by twice pi into R. U as 47.94 into 60 divided by 2 pi into R is 0.45 meter. If you do the calculation, you will get 1017 RPM. Therefore, I got another answer. N is 1017 RPM. Now I'll have to evaluate M dot, mass flow rate through the bucket, and that's through the nozzle. So we know the actual eta W. So I can write now eta W actual is equal to power divided by power produced divided by half M dot mass flow rate to the bucket C1 square, or mass flow rate through the nozzle M dot. So from here I can calculate M dot as P divided by half eta wheel efficiency actual into C1 square. So that is, power is given as 1250 kilowatt. So you multiply it by 10 to the power 3 divided by half eta W actual I have evaluated as 0.837, and C1 is as 102, so that is square. If you do the calculation, I have got M dot as 287 kg per second. So M dot per nozzle would be equal to 287 divided by 2. It will be 143.5 kg per second. Thus I have evaluated mass flow rate for a nozzle which is 143.5 kg per second. Now if I use the continuity equation, I can write M dot mass flow rate in a nozzle is equal to rho C1A. A is the nozzle flow area. So that also can be written as rho C1. C1 is the absolute velocity of jet. If the diameter of the jet is a small d, that I can write pi d square divided by 4. This is the area. Now from here I can evaluate d. So d can be expressed as root over 4 m dot divided by pi rho into C1. Put the values of all the quantities. If you do that, then root over 4 m dot is 143.5 kg per second divided by pi into rho 10 to the power 3 into C1 is 102 meter per second. If you do this calculation, you will get D as, so I have got D here. From this I have got D as 42.3 millimeter. So this is the another answer. The diameter of the jet here is 42.3 millimeter. So thus I have solved the problem. I have solved two problems here pertaining to Pelton wheel. Thank you for listening.